Solutions. This is basically part of Chapter 4 and Chapter 13, but just a little bit of 13. So based on what you did today, you should have a pretty good working definition of a solution. Now, a couple of things that we didn't really spend a lot of time on, but I want to remind you about are two ideas, solvent and solute. Now, the solvent does the dissolving. In this case, when you look here, you see water is the solvent. It's literally pulling the sodium chloride ions out and putting them into solution. So it's the solvent, it's what does the dissolving. The solute, on the other hand, is what's dissolved, so it's the sodium chloride. So the solute is dissolved, the solvent does the dissolving. Now, a couple of points. The salt separates. This was what was known as dissociation. So we knew it was dissociated because it produced electricity, which brings us to the next point, which is electrolytes. When we talk electrolytes and non-electrolytes, again, remember that we are talking about that conductance of electricity. The electrolyte conducted, the non-electrolyte didn't. Notice that they both dissolve in water. In fact, when we talk about non-electrolytes, these are all your molecular compounds. Electrolytes are all ionic compounds. Well, let's specify. All soluble ionic compounds. They're electrolytes. But there are a few molecular compounds that are electrolytes. They're considered strong or weak, and this has to do with the acids and the bases. So strong acids, strong bases, weak acids, weak bases are molecular compounds that are also electrolytes, slight electrolytes in any case. Now, a couple of points. For anything to form a solution, you have to have an attraction. They have to be attracted by the solvent. There has to be that breakdown, that adjustment. It has to be more attractive in the solvent than it is to each other, and that's literally what's going on. So when we talk about how a solution is formed, it literally pulls it out. One of the things to note here and here is how they show that each ion is literally surrounded by the water molecules. So dissociation was when the ionic compound broke down and separated, but the reason it does, how it does, is simply because of these attractions. Now, one of the things that we're not going to spend a lot of time talking about here, but you need to remember, from previous class, water is polar. So if water is polar, that means it has that slight charge, and it is that slight charge that makes all the difference. So notice here, I have sodium and chlorine. Okay, that sodium ion is surrounded by the oxygens, which were the negative pole. Okay, the chloride ion, which is negative, is surrounded by the hydrogens, which were the positive pole. So that's kind of what's going on, and that's laying the groundwork for what we'll be talking about later, but this is what's going on. This is what you all have to be able to recognize and draw. We're going to quickly sidestep into types of solutions. Types of solutions have to do with the amount that's dissolved, so that dissolved amount of solute. Now, one of the things to remember is a saturated solution literally holding all that it can. Unsaturated solutions aren't holding everything they can. So when you look at the diagram here, this is where you should hearken back, shall we say, to biology. And in biology, you talked about isotonic solutions, hypotonic solutions, and hypertonic solutions. The point, if you've read the learning objectives, is to recognize that you should be able to diagram, in essence, what would be a hypertonic solution, a hypotonic, or an isotonic. In terms of what we're talking about, you can think of a saturated solution as isotonic. Hypotonic would be very little solute. Hypertonic could be thought of as supersaturated. Now, the big difference in biology, these terms iso, hypo, and hyper were relative. So for example, a saline solution is a salt solution, fairly salty. But that saline solution is isotonic with your eye, meaning the concentration of solutes in your eye is the equivalent of the concentration of solutes in that saline solution, therefore it's isotonic. This was real important in terms of biological systems because hypotonic and hypertonic could drastically impact the health of the cell or even whether the cell would continue to live or not, because it had to do with that movement of water, that osmosis and movement of free water molecules. So, three types of solutions again: saturated, unsaturated, and supersaturated. Supersaturated it's what's behind a lot of candy making. You get that seed crystal, you do rock candy. If you've ever put the string in a really supersaturated sugar solution, you make rock candy. So you probably did that in elementary. Now, aside from just saying supersaturated, unsaturated, or saturated, we have the actual math behind it, and that was the molarity. Now remember, molarity is moles of solute over liters of solution. Now, volume is temperature dependent, which we don't often think about, but it is. We know it is. So molarity can change with temperature because molarity impacts that volume. All right? Now, when we talk moles of solute and liters of solution, in essence, keep in mind we're talking moles per liter. And remember, it's liters of the entire solution, not just a part of it. Now, that's contrasted with molality, where we're dealing with moles of the solute over kilograms of solvent. Okay? And that's why molality is sometimes preferred. Now, molarity is what we're going to be dealing with a lot in this section because we're going to be dealing with aqueous chemistry, aqueous meaning solution chemistry. And so molarity is what we're going to use for a lot of that. So you want to be real familiar and comfortable with this. Now, second side step here is colloids. The big thing to remember about a colloid, a solution, a suspension, is it really has to do with the size of the particles. This is a real nice table. Again, this is that other part of that little bit in chapter 13, but it shows you the phase of the colloid, what's dispersing. Now, by dispersing, we're talking about light. Colloid disperses light. So you can see here how that light's getting spread out, but you don't really see it. You know there's light passing through, but it's not spread out. This dispersion effect here is what's known as the Tyndall Effect. That is exclusive to colloids, and that's one of the ways we tell a colloid from a suspension, from a solution. Okay, and so the last thing then is the suspension. And basically, the best way to explain a suspension was with a joke. So when we look at a suspension, think of it as muddy water. You can shake it up, it looks like it's all mixed, but eventually stuff settles out. And the stuff that settles out then is what we call the suspension, because the particles can be seen, and in fact the particles are big enough that they don't really stay in solution. That's one of the biggest differences between a colloid and a solution. In a colloid, I can't physically see the particles, but I can see the particles scatter light. That's how a colloid is different from a suspension. So when we talk colloid suspensions and solutions, it really has to do with that size of the particle and how dissolved they are, how mixed they are, because a suspension is definitely not well mixed, and a solution is the best mixed homogeneous matter because it's mixed at the molecular level, because the ions or molecules are completely surrounded, they are solvated by the solvent.